Solving general chemistry problems. Electrochemistry. Here's a schematic representation of an electrochemical cell. Give the description for this cell using standard cell notation. Provide a reaction description for the anode and for the cathode. Notice that the voltmeter reports a voltage of plus 0.46 volts. Since the copper electrode is connected to the negative terminal of the voltmeter, we can identify it as where oxidation is occurring, and hence as the anode. Silver must be the cathode. In standard cell notation, we would write this as copper solid in a copper 2+ solution with a concentration of 1 molar, separated by a salt bridge from a solution of silver plus at a concentration of 1 molar, and finally a silver solid electrode acting as the cathode. Now, from the composition of the salts added, copper nitrate and silver nitrate, we can see that the solutions must be of copper 2+ and silver plus. We can write out the appropriate reactions in each cell. Don't forget that the reaction at the anode is an oxidation. Electrons will appear on the product side of the reaction, and the cathode is where reduction occurs. Electrons will appear on the reactant side. The question does not require us at this point to ensure that the electrons balance in the two reactions. That would only be necessary if an overall reaction equation were requested. Therefore, the two reaction equations are given here. Now, here is another cell to consider. Give the description for this cell using standard cell notation. Provide a reaction description for the anode and for the cathode. Now notice that this time the voltmeter is reporting a negative voltage, minus 2.42 volts. A negative voltage means that the connections to the voltmeter have been made incorrectly. The electrode at which oxidation is occurring has not been connected to the negative terminal. Now the cell is working just fine. Chromium metal is being oxidized to chromium ions, and gold 3+ ions are being reduced to gold. However, when the voltmeter was connected, the negative electrode was mistakenly connected to the positive terminal, and vice versa. The cell chemistry is proceeding just how it wants to. Oxidation is occurring at the chromium electrode. This does not change just because someone hooked up the voltmeter incorrectly. So the chromium electrode is the anode. We can rewire the voltmeter to the cell so it is correct. We would then observe plus 2.42 volts for the measured potential. The cell would be written down as chromium solid in a chromium 2+ solution at a concentration of 1 molar, separated by a salt bridge from a solution of gold 3+ ions at 1 molar, and a gold electrode functioning as the cathode. The reactions are the oxidation of chromium to chromium 2+ and the reduction of gold 3+ to gold metal. Now, a word of warning here. Sometimes problems in general chemistry can be presented in a confusing way. For instance, imagine if a question were asked as follows. The following cell was set up and the gold electrode was connected to the negative terminal of a voltmeter. The measured cell voltage was minus 2.42 volts. Which metal electrode is the cathode? Now this was, of course, the arrangement we had at first. The problem with the question is that the standard cell notation convention asserts that the electrode on the left is the anode, which means that oxidation is occurring there. From that alone, it would be understandable to specify the chromium electrode as the cathode. If this were the case, then connecting the gold to the negative terminal should have produced a positive potential difference. That it was measured to be negative, however, implies that things should be reversed, and that is what we did. The problem with the question is mixing up the standard cell notation in a non-standard way. A better way of wording the question would be, a gold 3+ electrode was connected in a cell with a chromium 2+ electrode. The gold was connected to the negative terminal of a voltmeter, and the cell potential was measured to be minus 2.42 volts. Which metal is behaving as the cathode? Now we are not biased towards either electrode being the anode by convention, and the negative potential tells us to switch polarity. The gold should be connected to the positive terminal, and therefore is the cathode. Watch out for these kinds of questions. They usually are expecting you to switch the connections, but remember that the chemistry of the cell is not changing just because you hook up the terminals incorrectly. So no matter whether you hook up the chromium or gold electrode to the negative terminal, reduction is still happening at the gold electrode and oxidation at the chromium. Standard cell potential notation would be the same regardless. Now here's another cell. As before, the description for this cell using standard cell notation is sought. Provide a reaction description also for the anode and for the cathode. This presents a new feature in cell design. The cathode uses a platinum electrode, but the platinum is not part of a redox process. Instead, it is a metal to conduct electrons, and also a catalyst for the actual redox process, the reaction of H+ ions and H2 gas. Because hydrogen is a gas, it cannot be used to conduct electrons to an external circuit. But a scheme whereby the platinum electrode is bathed in hydrogen bubbles at a pressure of 1 bar, while immersed in a solution that is 1 molar in H+, allows the reduction reaction to occur under standard conditions. The other electrode is like the ones we have seen before, except it is using aluminum as the metal, and aluminum 3+ in the solution. In standard cell notation, we would write solid aluminum is the anode, a phase boundary to the solution which consists of aluminum 3+ at a concentration of 1 molar, then a salt bridge, then a solution of H+ at 1 molar, a phase boundary to gas phase hydrogen at 1 bar pressure, and finally another phase boundary to the solid platinum cathode. The measured cell potential is positive, so we have correctly connected the cathode to the positive terminal, indicating that the platinum cell is where reduction is occurring. Oxidation is occurring at the aluminum electrode. Here are those reactions. In the hydrogen cell, the platinum is referred to as an inert electrode, meaning it is not directly part of the redox process. It is present as a conductor and as a catalyst. Carbon is sometimes used in other situations as an inert electrode. This is an example of a gas electrode. Hydrogen is widely seen as the most common example, but the concept could be used with other gases such as oxygen. Here is another cell. Same request as before. Now this presents another feature that can show up in these cells. We could have created a cell with silver ions and just a silver electrode, but the electrolyte, the solution, in the silver cell only has H+ and chloride ions. Notice that there is a coating of another solid material, silver chloride, on the silver electrode. From what you know of oxidation states, you can see that the chloride ion is not changing its oxidation state. It is the silver that exists as silver 0 and silver 1+. But the different oxidation states are both in solid state phases, though they are different phases. This cell would be described as follows. A cadmium electrode has a phase boundary with a solution of 1 molar cadmium ions. A salt bridge separates that compartment from another containing chloride ions with a concentration of 1 molar. A phase boundary connects to a solid silver chloride phase, and another phase boundary connects to a solid silver electrode, which is the cathode. We know it's the cathode because the measured cell potential is positive and it is connected to the positive terminal. Here are the reactions at the 2 electrodes. We have now seen electron exchange between 2 solid phases, between a liquid and solid phase, and between a gas and a liquid phase. Here is another common type of electrochemical cell. Same requests as before. This time the feature is that another inert electrode is being used, but the electron exchange involves 2 oxidation states of the same ion dissolved in the electrolyte solution. In fact, both electrodes are inert platinum electrodes. The first is the same hydrogen electrode we counted before. The second now has 2 oxidation states of iron in the solution iron 3+ and iron 2+. They now use the platinum electrode as a catalytic site with which to exchange electrons with the circuit. Again, the measured cell potential is positive, so the electrode at which reduction is occurring is correctly connected to the positive terminal. The iron cell, therefore, is acting as the cathode. The cell would be described as follows. Platinum electrode with a phase boundary to hydrogen in the gas phase at 1 bar pressure, another phase boundary to a solution with 1 molar H+ ions, a salt bridge to another solution with both iron 2+ and iron 3+, each at 1 molar concentration, and finally another phase boundary to another platinum electrode, which is acting as the cathode. And these are the reactions occurring at the 2 electrodes. As you can perhaps appreciate, it is difficult to continue to draw out each of the electrochemical cells. The standard cell notation greatly improves the ease with which we can discuss and study an electrochemical cell. From now on, we will use the cell notation, but hopefully you are now able to envision what that notation implies.